So I want to look at the second problem in the homework, number 9. And here we're talking about problems with a phone line. So it says a problem with a phone line that prevents a customer from receiving or making calls is upsetting to both the customer and the telecommunications company. Then they give us this data file. It contains samples of 20 problems reported to 2 different offices of a telecommunications company and the time to clear these problems from the customer's lines. Now it's important to understand that these 20 problems are not the same problems that are shared between 2 different telecommunication companies. Okay? Well, actually, they're 2 different offices of a telecommunications company. And it turns out this word samples is really important. So this tells us that there's more than one sample of 20 problems. Okay, so that's important to know because this goes to the question of whether or not we're looking at a paired t-test or an unpaired t-test. That is, are the populations independent or are they not independent? Okay, so we know in this case that these 2 populations are going to be independent. Okay, let's go ahead first and get the data file. So we want to go to StatCrunch. Let's see. Do it this way. And we're going to go to phones in chapter 10. My stat lab. And let's see. Go to the home. Okay, now we want to go to StatCrunch, and we're going to go to chapter 10. The data set's called phones, or phone, and there we are. Okay, now it's going to cut and paste it in the Excel. We should have 20 data values, and we, oh, that's because they're listed between the different companies. Okay, so I'm going to go ahead, I'm going to select them all and cut them, and then I'm going to go over here. So this is going to be a little awkward. So I'm going to do this company 1 and company 2. Okay, and then we'll paste this. And basically all I want is I just want the times. So I'm going to go ahead and cut all these. And then paste this up here. Okay. And then I'm going to cut everything else out. Alright. And I'm going to add, just because this tends to be a little easier to do, I'm going to compute my statistics here on the side. So what do I know I need? Before I really do the problem, you know, they want us to look at, they want us to do a hypothesis test. So I know I'm going to need X bar from each of these samples. I'm going to need the sample standard deviation. I'm going to need the sample size, which in this case is 20 for both. Oops. Okay, and we'll start from there. So let's see, this is going to be equal to average. Oops. And go ahead. And I can just, excuse me, I can just drag this over, and I'll do it for the next company. And then we do sample standard deviation. And same thing. Okay. And then drag this over. And we'll just shade these in slightly differently. Okay, so there's our sample statistics. I'm going to take this out too. I don't need this particular row. Okay, so that looks good. And just to make sure and check, it should have gone from 2 to 21, and it did. Okay, so that's basically the data. So now I want to do a hypothesis test. So we're going to have to assume that the variances are equal to use the unpaired t-test, okay? And this is kind of another clue that this is not a paired t-test. This is not a situation where we're looking at related samples from a related population, because we don't need to know anything about the sample. We don't need to know anything about the variances of the individual samples, because we're only interested in the standard deviation of the difference. Okay, so this is kind of a second clue. But let's go ahead and do the hypothesis test. Before I do that, though, I know that I'm going to have to compute the pooled standard deviation. So I'm going to go ahead and just do some quick calculations to get that done. One of the terms I know that I need is I need the numerator and the denominator. So I'm going to do the numerator here, and that's just going to be equal to. The nice thing is I only have to compute this one time, and then once I compute it one time, I can just drag it over for the other term. Okay. So I'm taking the standard deviation of each sample, squaring it, and multiplying it by n times 1. And I'm going to drag this over like this. Okay. And I'm going to add these. And the denominator is just always the sum of the two sample sizes minus 2. That should be 38. And now we're ready for the, now this is going to be the pooled variance. So let me be a little more careful. I'm going to call this the pooled variance. I'm going to compute the pooled standard deviation, because that's actually what I'm going to need in this problem. Okay, so I'm going to go ahead now. So SP, the pooled sample standard deviation, is equal to the square root of okay, and it's going to be both of these terms in the numerator added. Okay, divided by the denominator. Actually, I am going to do the variance because, yeah, that's okay. I'll leave it like that. Okay, that's my pooled sample standard deviation. And notice that it's between these two values, so that's good. It's kind of nice to do this if for no other reason than just for a check. Okay, so now I have everything I need to do the hypothesis test. If I wanted to, I could compute the standard deviation of the difference. I may just do that really quick. Standard deviation of, x1 bar minus x2 bar and it's because it's going to show up in both the confidence interval and the hypothesis test, so it's just easier. So remember, this is going to be the square root now of this squared, divided by n1 plus the pooled standard deviation, pooled sample standard deviation squared, divided by n2. Okay? Now this should always be less than any of these, because this is a standard deviation of the estimator. That's always going to be smaller, okay? Okay, so let's do the hypothesis test. We have everything we need for all the different parts of the problem now. We're all set up. Okay, so first we're going to do the hypothesis test, so we have to state our hypotheses. And we notice that we're looking to see if the difference in the means are, if the difference in the means are different. Okay, is there a difference in the mean waiting time between the two offices? So here I'm going to express the null hypothesis as mu1 minus mu2 is equal to 0. I always want to put this d on the right hand side. This difference that I'm testing x1 bar minus x2 bar against. Okay. And of course the alternative is that they're different. So I can just cut and paste, hit enter, go down here, and just say not equal. All right. Next thing I have to do is I have to compute my test statistic. So I know in this case that it's going to be a t-test statistic, and it's going to be equal to x1 bar minus x2 bar divided by the standard deviation of x1 bar minus x2 bar. That's a very small t value, right? Because I've already calculated standard deviation of x1 bar minus x2 bar, and I didn't have a d here because d was equal to 0. Okay, let's go ahead and compute the p-value. So we're doing a two-sided test, and we have a positive test statistic. So remember that this is going to be 2 times 1 minus. And now I'm going to do t dot dist. There's my test statistic. I have 38 degrees of freedom, and it is cumulative. Okay. And it's going to be very large. Okay. So my decision rule is actually quite simple now. Because I have that p, which is equal to, and we can round this off, it doesn't matter, it's so large, right? 0.73 is greater than or equal to 0.05, which is my alpha in this case. So I'm going to fail to reject the null hypothesis. Okay, now finally we have to state our conclusion. So we have to go back and ask ourselves, okay, what were we studying? Well, the time to clear the problems in these two offices, right? Okay, so we might say something like this. We might say at a significance level of 0.05, there is not sufficient evidence to conclude the, and what is it exactly we're looking at? The time to resolve the problems, right? So we'll say to conclude the resolution time. And we have to be a little careful. We have to say average resolution times between the two offices are different. Okay, and that's it. So there wasn't sufficient evidence to conclude that the average times were different. Okay. P-value, they make a big deal about this. We computed the p-value, and the meaning is that it's the probability that we could get a test statistic. Okay. In this case, 0.725. That's as far from 0 or further. Okay, part C, they want us to make a confidence interval. And it's going to be 95%. This actually is really easy. We've already computed everything, okay? So for part C, we need the margin of error. So we know that we're going to need the critical value. Let me put here. So I want the 95% confidence interval for mu1 minus mu2. Alright, so let's go ahead and compute our critical value first. We know that the confidence, whoops, type in the wrong place. Is 95%. So now we can compute the critical value from that, right? Now the critical values is basically going to be the value that corresponds to the 2.5th percentile for a random variable coming from a t-distribution with 38 degrees of freedom. Okay, so this is going to be t.inv. And I'm going to take 1 minus this and divide it by 2. Usually I would do this outside of this bracket, but it's okay. And we had 38 degrees of freedom. And it's going to be a negative number, but when I do the margin of error, I'll take care of that. So remember that the margin of error is equal to the critical value times the standard deviation of x1 bar minus x2 bar. And I already computed the standard deviation of x1 bar minus x2 bar way up here just for that reason. And that's my margin of error. And now I'm ready to get the lower and upper endpoints. So the lower endpoint, is going to be x1 bar minus x2 bar minus the margin of error. Okay, and the upper endpoint, I just add the margin of error. And so this is the 95% confidence interval for the difference in the two means. Now, important, if I ask you what is the relationship between the confidence interval result and the hypothesis test, remember that failure to reject the null hypothesis when, in this case, d is equal to 0, can only happen if and only if 0 is in this confidence interval, and it is, the 95% confidence interval. And it only applies when the alpha and the confidence add up to 100%. So in other words, the alpha for the hypothesis test plus the confidence for the confidence interval have to add up to 100%. Then it's true that that you're going to reject the null hypothesis, that your true parameter is equal to d if and only if d is in the confidence interval. All right, I think that's all for this problem.